Okay, so the answer to A would be the voltmeter. B is the hydrogen half cell, so B should be a platinum electrode, anything that is inert, because you don't want it to disturb your hydrogen gas, hydrogen plus half cell. C would have to be your H plus ions, and it would have to be in 1 mole per dm cube. And D is your lead Pb slash Pb2 plus half cell. So you would want that electrode to be your Pb solid. Okay. The next question is what I want to look at. The E note for Pb2 plus Pb electrode is 0.13 volts. So I like to refer to the half cell equation. So I should be looking at this Pb to Pb2 plus. And then I want to know the effect of the electrode potential. Okay, so if the question mentions electrode potential, then we are only looking at E, okay, not E cell. If it says cell potential, then that's where E cell comes in, okay? So the E node, predict the potential of the right-hand electrode in the diagram above. So the right-hand electrode is referring to this half cell, okay? It's on the right side. What happens if you use a saturated solution of PbCl2? Now, remembering that PbCl2 is made up of Pb2 plus and Cl minus. Okay, so the one that we're interested in is the Pb2 plus. The concentration of your Pb2 plus is now 3.5 times 10 to the power of minus 2, which is smaller than 1 mole per dm cube. So that means the effect is decreasing. The effect is the same as decreasing the concentration of Pb2 plus. Le Chatelier's principle said that if you decrease the concentration of Pb2 plus, the system will try to increase it by favoring the reverse reaction and to produce more Pb2 plus. Okay, that means if you are favoring the reverse reaction, you are going backwards. You're making the electric potential more negative. Okay. Also, another explanation is because you're producing more electrons, so your system will be more negative. So if your E node is negative 0.13, your E, which is under non-standard condition, okay, so this is standard, and this is non-standard because you have changed the concentration. Instead of using 1 mole per dm cube, we now use something smaller, 3.5 times 10 to the power of minus 2. Okay, so we say that it will be more negative. Okay, so you would expect the number to be more negative than negative 0.13. And if you look at that list, you only have one option. Okay, negative 0.17. Is that okay? Okay, so if the question is not asking for the effect on E cell, it's easy, it's straightforward. You don't have to worry about the E cell calculation. The explanation for this, we say that, okay, so concentration of Pb2 plus decreases. So the equilibrium favors backwards reaction. Yeah, that should be fine for 1 mark. 1 mark for the correct value and another mark for the explanation. Okay, so I'll just zoom this out, let you copy for a while I take the attendance. Whiskey, Danish, Apple. How do I make this? I see the full name. Let's see full name. If you're done with this, I would like you to read the same question 19C. Okay, have a look at question 19C. So we're missing 3 people. I cannot see your full name. Who is Mohammed? Oh, wow. I see Risky. There's another Muhammad, BE4. I cannot see your full name. Oh, wait, I can. Oh, yeah, D. All right. This is another Muhammad. Tamizi. Okay, so I am missing read 1. Hazira is not here. Is Dania here? So that's 9, 10, 11, 12. Okay. Right. Part C. The behaviors of PbCl2 and SnCl2 towards reducing agents are similar, but their behaviors towards oxidizing agents are very different. So the species that we are interested in is actually not the chloride, but it's actually the Pb2 plus and the Sn2 plus. Their behavior towards reducing agent, that means they are being reduced. Oops. They are being reduced. Okay, but their behavior towards oxidizing agents means they are being oxidized. So I need a few equations and values. Illustrate this comparison by quoting and comparing relevant E-note values for the two metals and their ions. Explain what the relative E-note values mean in terms of the ease of oxidation and reduction. So we have to comment how easy or how difficult they are being oxidized or reduced. So I am interested in Pb2 plus. So if you see Pb2 plus here, and there's another equation that involves a Pb2 plus, going forward is reduction, and going in reverse is oxidation. So I need these two half equations because we're talking about both the ease of oxidation and the ease of reduction. Okay, so I'll have that somewhere here, maybe here, so I can have space. And the other one is Sn. Sn, same thing. I am interested in Sn2 plus. So one Sn2 plus is on the left side, which means the value uh, when it is being reduced, and the other Sn2 plus is on the right side where it will be oxidized. Okay, so I will use this. I'm going to do that. Okay, so the statement says that the behavior of Pb2 plus and Sn2 plus to reducing agent, that means the ease of reduction. Look at the value when Pb2 plus and Sn2 plus is being reduced. They have more or less the same value, negative 0.13 and negative 0.14. Okay, so we need to comment on that. Hello, Dania. Thank you for joining. Siapa lagi parameter? Okay, Ridwan is here as well. All right. Okay, so how do we comment the value? We say that first we talk about the ease of reducing. Why the statement says that they behave the same way towards the reducing agent. We can say that Pb2 plus and Sn2 plus behave the same towards reducing agent because the E node are negative 0.13 volt and negative 0.14 volt respectively. Okay, so the numbers are quite close to each other, so you would expect them to behave the same way, or you would expect them the ease of reduction is also similar. Okay, now I want to look at their behavior towards oxidizing agents. That means their ease of oxidation. Okay, so you can see that Pb2 plus going to Pb4 plus, that is an oxidation process. Sn2 plus going to Sn4 plus, that is also an oxidation process. And the number is very different, 1.69 and 0.15. Now, if you want to talk about the ease of oxidation in the early part of these notes, we say that the more negative um, the more negative the E node is, the easier or the more likely it will be oxidized. Okay, so if we compare Sn2 plus and Pb2 plus, it looks like Sn2 plus, since it is more negative, okay, or even though it's not a negative number, but because it is more negative, then it is easier or easily oxidized compared to Pb2 plus. Okay, so we will mention that the E node of Sn2 plus is positive 0.15 volt, which means it is more likely to be oxidized to Sn4 plus compared to Pb2 plus, which has an E node of 1.69. So we say that Pb2 plus less likely to be oxidized to Pb4 plus. Okay, so don't forget, the more positive your E note value is, the more likely it will undergo reduction. The more negative your E note value is, the more likely it is to go oxidation. Okay, I know that both of these numbers are not negative at all, but if we were to compare the relative values, um, SN2 plus is more negative than Pb2 plus. So SN2 plus is more likely to be oxidized to SN4 plus compared to Pb2 plus to be oxidized to Pb4 plus. Okay. Okay. I will skip the balanced equation. I will now move on to the next question, which is question 20b part 2. Okay, question 20b part 2. If you're done copying this down, please move on to 20b. So we'll skip the first part. This is an E cell comprising of a copper 2 plus copper half cell and Ag plus Ag half cell. Okay, we skip the label. If you read part B, it says that the above cell is not under standard conditions. Okay, because the Ag plus is in a saturated solution, which has a value of less than 1 mole per dm cube. The electrode potential E is given as the equation below. Okay, use the data booklet to calculate the E cell if the E cell was operating under standard conditions. So I will just give you the answer because I am pretty sure that you can, by now, you should be able to work out the E cell of the equation. Okay, in the above experiment, the E cell was measured at 0.174. So this is the E cell of standard condition, whereas this 0.17 is at non-standard condition. Okay. Even though we are not using standard condition, but I always need my half equations. So I still need my silver ion, silver half equation. I'll just put it here. And the other one, the other side would be the copper. Oops, sorry. Okay. So they want us to calculate the value of the E electrode potential. Okay, so E note is standard electrode potential, but we want to find the electrode potential in non-standard for the Ag plus and Ag electrode. Okay, so we cannot use this expression yet because we don't know the concentration of Ag plus in the saturated solution. Okay, but what we do know is that our copper solution is not affected. Okay, copper solution is under standard condition. It stays as 1 mole per dm cube. Okay, so if we know the E cell as 0.17 volt, and we know that E cell calculation is equals to E reduction plus E oxidation, and based on this number, we can see that the Ag plus Ag half cell is more positive So this is where reduction is happening. Is it mentioned here? Not mentioned. Okay. And the copper 0.34 is where the oxidation is happening because it is the negative terminal. Okay. So as I said, copper has no effect. We are not changing the concentration of copper. So our electrode potential of reduction is 0.3. Salah. Okay. The electrode potential of reduction is what we want to find because we don't know the value, right? But electrode potential of oxidation, which is of the copper, is negative 0.34. Okay, because copper stays under standard condition. So the E naught value stays as 0.34. That is if we are looking at reduction. But since at the copper half cell oxidation happens, I have to swap the number negative 0.34. Okay, so I have to work out my X to find the non-standard electrode potential for my silver half cell. Okay, and that should give me let's see. Where am I at right now? B part 1. 0.51 volt. So my E of reduction is 0.51 volts. So you compare the value of my electrode potential under standard condition for silver is 0.8, and then under non-standard condition it's 0.51. So that means it has now becoming more negative. Okay. As you would expect, because our concentration of Ag plus decreases, okay, and Le Chatelier's principle says that we need to increase back the concentration of Ag plus. We are producing electrons and we are also favoring the backwards reaction. So we should expect our electrode potential to become more negative, which is shown and proven by this number. At standard condition, it's 0.80. At non-standard condition, that means when you are using the concentration of Ag plus to be less than 1 mole per dm cube. Okay, it doesn't say how much, but it's less than 1 mole per dm cube. It's the same effect as decreasing the concentration. Okay, I will skip part 3 because part 3 is just using this expression to find the concentration of Ag plus. All right, you already know your E electrode, which is 0.51. You know your E naught electrode, which is your 0.80, and you can solve your Ag plus. Okay. Next question I want to look at is question 23B. Wait, we are at question 21A part 3. Okay, 21A part 3. Basically, we want to know the effect of increasing the concentration. Okay, so I like to do this question because this is a question where students always make mistake. Okay, so the next question, 21A, part 3. By using one of the phrases more positive or more negative or no change, deduce the effect of increasing the concentration of OH minus ion on the electrode potential. So again, we're not looking at the E cell, we just want to know the effect it has on the electrode potential, which is your E. Okay, of course, you need to know your half equation. Now, even though the equation is given to you already here, but bear in mind, these equations are not in equilibrium. It is given as a single arrow. So do not fall for this trick. Always use the equation in the half cell. So left-hand electrode is the one with hydrogen. Um, hydrogen and hydroxide ions, so it is this one, to form H2O and 2 electrons. As for the right hand electrode, okay, so I'll just put it somewhere here. That's not the answer. Make sure you don't get confused. Where can I put this? Let's see. The other equation would be the oxygen with water. So it will be somewhere here, I believe. Oxygen with water to form 4 hydroxide ions. Okay, so you need to choose the correct half equation, because if your half equation is wrong, then everything else will be wrong. Okay, so the first, this is our left hand electrode and this is our right hand electrode. Okay, so first we want to look at the left hand electrode first. What effect does it have on the E note values? So these are your E note values when you increase OH minus. Okay, so looking at the first half equation, increasing OH minus means you are favoring the reverse reaction, correct? When you reverse reaction, that means you're going backwards, you are becoming more negative. Another reason to look at that is because you're producing more electrons, so you are becoming more negative. So easy, you just answer more negative. Okay, next is the right hand electrode. What happens when what happens when the concentration of hydroxide ions increases? Okay, so this time you are increasing OH minus, which is the same thing. And again, increasing OH minus, Le Chatelier's principle will try to reduce it or decrease it by favoring the reverse reaction. So you would expect your E note electrode potential value to be again more negative. Okay. So hence deduce whether the overall E cell is likely to increase, decrease, or remain the same when OH minus increases. Explain your answer. Okay, so this time it's a little bit tricky because if you look at the overall equation, do they want you to write down the overall equation? I believe. Okay, so if you look at this equation, it looks like, oh, if I am increasing hydroxide ions, the added effect would be more negative. However, don't forget that on the left hand side, what's actually happening is you are taking the oxidation process. Okay, so oxidation process means you are taking the opposite value. So if your E note is becoming more negative, the E note of oxidation is now becoming more positive. Okay, for example, more negative would be negative 0.90. That is for reduction. For oxidation would be 0.90, which is now becoming more positive. So if you have an effect of more negative and more positive, of course the net effect will change. Okay, another way of seeing this is look at your hydroxide ions. They appear in both sides of the equation. So if you increase both, concentration of OH minus favors forward, favors backwards, then the effect cancel out. Okay. Deduce whether the overall E cell. Okay, so E cell will be no change to E cell. Okay, explaining your answer. This is part 4. So how can we explain our answer? The okay, so OH minus is present on both sides of the overall equation. So the effect cancel out. Okay, so if you're wondering which equation I'm talking about, it's this one. OH minus on the left, OH minus on the right, and you increase them by the same amount. So favor forward, favor backwards, then it cancels out. Oh, sorry, this should not have the standard symbol. Okay, please remove the standard symbol because that is no longer in standard condition. Okay, I will leave this on for you to copy. Next question I want to look at is 23 part B. Question 23 part B. Where's part B? Okay. Predict the outcomes, is it? Yes, it's predicting the outcomes. So here we have a cell that is made up of, again, copper 2 plus copper half cell, and the other one is M2 plus and M. So this could be any metal. Use the data booklet to calculate the standard electrode potential of M2 plus and M system. Okay, right. So this time, they don't want us to find the E cell. They give us the E cell value, and they give the value of one of the E nodes. So we have to find the electrode potential of the other half cell. Okay, so moving on to question 23, part B. The standard cell potential was found to be 0.76 volt. That means E cell is 0.76 volt. And we know that E cell is E node reduction plus E node oxidation. And the copper foil was the positive electrode. So that means this is the positive terminal. This is where reduction happens. Okay. We will need the value for the copper 2 plus copper half cell, which is, so you can see how much I utilize my data booklet, and you should do the same as well. Okay, always use the equation on the data booklet. Use the correct equation, of course. Don't just simply use blindly. Right, so since I know my copper is reduction, so I take the value as it is. That means 0.76 is equals to reduction 0.34 plus X, where X is my E note of oxidation. 0.76 minus 0.34 is equals to 0.42. Now remember, this is oxidation. That means if we were to write down the E note value, we have to reverse the sign. Just like how we reverse the sign when we are given or when we use the value in the data booklet. Okay, so E note values are written as reduction. Okay, so we want it to be in this form. All the numbers here are the numbers representing the forward reaction, which is the reduction reaction. So we have to change the sign so that our E note values is written as reduction. Okay. Use the data booklet to calculate the standard electrode potential of the M2 plus M system. So that means this is our unknown. We do not know the electrode potential of the oxidation, but we found that for oxidation, it's 0.42. That means for reduction, it's negative 0.42. So E note is equals to negative 0.42 volts. Okay. Is everyone following so far? Are you all okay? Okay.
Yes. Okay.
Thank you. Which question of thought? 23B. Which one? Let me see part 3 if I want to go through that. I think part 3 is fine. You should be able to understand and write down the equation. So after this question, I will move on to question 30. So if you want to find what the metal is, I don't know if we can find it. Negative 0.42. Do we have a metal with the value negative 0.42 in here? Mm, now the closest one that is not here. Maybe it's Fe. Possibly that's the closest one that I can think of. That metal M is most probably, but I cannot confirm, is Fe. Okay, right. If you're done with this question 23B part 1, I would just like to touch on that. The rest of the question, I'll let you try. So let's now move on to question 30. So I tried to skip as many questions as I can so we can. Oh, this is actually. How come I didn't include this? Sorry. Before we go to question 30, can we just. Is it correct? Oh, 29. Okay, question 29. Question 29 is interesting. Just the first part. 29 part 2. Okay, so we've got um three redox systems here. Okay, they are all the methyl Ru ruthenium. Okay, but the only difference is the one in the bracket. This is what we called ligands. Okay, so you will look at ligands later on in the next two topics, if I'm not mistaken. Okay, so they're very different. Ruthenium with water, ruthenium with ammonia, and ruthenium with En. Okay, ethyl diamine, but the short form is En. And also, the most important thing is their oxidation state. Oxidation number is different. Okay, so +2 and +3. So you don't have to worry about them. Just for now, we just assume this as the half cell of ruthenium with water, which is what I will refer to as water, and then ruthenium with ammonia. I will refer it as ammonia, and then with En. Okay, so you've got two different cells here. First, we want to look at the cell for a system between En and ammonia. Okay, so you can see that between En and ammonia, En is more positive than ammonia. Okay, so that means it looks like this is the most negative, right? Because that is all I have to do. I want to know, I just want to arrange their qualitative values. I don't have to find the quantitative values. Okay, so it looks like En is more positive than ammonia, but is En more positive or less positive than water? Okay, so if you look at the second half cell, this time, so you see this time En is negative. So that means En is not the most positive, right? So water is the most positive among all. And we know for sure that ammonia cannot be more positive than water because ammonia is already more negative than En. Okay, so the arrangement is, if you can see, most negative. The redox system, how do they want you to write it down? Let me just see. 29. The most negative. Oh, my numbering system is Salah. Okay. Here it's question 29. Right. The most negative system is the one with ammonia, which is B, followed by En, which is C, and the most positive is water, which is A. Okay, so that's how you answer that question. So this is actually 29, and this would be 31, 33. Okay. That's, I don't know if that's something chemistry related or if that's just like a common sense. Okay, you just arrange which one is more negative, which one is more positive. Okay. The next question that I want to look at is question 31D. 31D part. Salah. 32, 32D part 3. Okay, 32D part 3. So moving on now to question 32. I think the numbering is a little bit messed up on my version. Bukan 30, sorry, bukan 32, I'm sorry. 31D part 3. Okay, it's 31. Question 31D. We'll try to finish this question just before you go. Okay, An electrochemical cell made by Fe3 plus, Fe2 plus, and then S2O8 2 minus and sulfate. Calculate the standard cell potential. Of course, I will just give you the answer. Standard cell potential, that is D part A, 1.24 volt. State the material. I will skip that. Describe one change to each half cell that would increase the value of the cell potential. So this is now the reverse question of what effect would it have on the cell potential when you increase or decrease the concentration. Okay, this time we want to know how you can increase the value of the E cell, whether you want to increase the concentration or decrease the concentration. Okay, in order to do that, we need to first find the relevant half cell equation. So that is Fe3 plus and Fe2 plus, and the other one you need the S2O8. So that should go under S2O8 and SO4 2 minus. So you can see there are a few versions of the half cells involving sulfur. Okay, and the E cell is equals to E reduction plus E oxidation, right? If you look at the values here, you can see that the sulfur, the one with the sulfur sulfate S2O8 2 minus, I'll just call it the sulfur half cell, is more positive. So this one will undergo reduction. And the Fe2 plus Fe3 plus is less negative, more negative or less positive, so it will undergo oxidation. I think the easier one to work with is the reduction. Okay, if you look at the E cell value, if you want the E cell value to be big, you would want your reduction, because it's a positive number, to also be big. Okay, more positive. So first strategy, we make our E node reduction more positive. So how can we make our E node more positive? Easy, we just favor the forward reaction. Favoring forward reaction means increase S2O8 2 minus, or you can also decrease the concentration of sulfate. Okay, you have freedom here, whether you want to increase S2O8 or decrease the sulfate. Either way, it will favor the forward reaction, and it makes your E node to be more positive. And if that becomes more positive, your E cell will also be bigger. So increase concentration of S2O8 2 minus, sorry, it's or decrease concentration of SO4 2 minus. Remember, the square bracket is concentration. Okay, now the other one is a little bit confusing because our oxidation value is usually the opposite. Okay, we want our oxidation to be um, small. Whatever the value is, we want it to be small, because it will be a negative number here. So if you put in negative 0.77, so you want this number to be small. All right. So how do we make 0.77 smaller than it already is? We cannot make it more positive, because if we make it more positive, for example 0.80, that means when we write it down as oxidation, it will be minus 0.80. And subtracting a big number will make your E cell smaller. Okay, so that means second strategy is that our E node oxidation must be small. Okay, and to make the E node of the oxidation to be small, we want to favor the reverse reaction. That means make it more negative. Okay, so what we can do is to increase Fe2 plus so it favors the reverse reaction, or to decrease Fe3 plus so that it favors the reverse reaction. Okay, so Fe3 plus Fe2 plus half cell, we either increase concentration of Fe2 plus or decrease concentration of Fe3 plus. All right, we whatever it is, we want to favor the reverse reaction. Okay. I actually have one more question, but let me just see what that question is. The last one, question 33. Is that correct? 33 ataupun is that 32? Hold on. 30. This one is question 31. Question 33 is. Mhm, I think it's that one. Okay, I think that should be okay for now. I'll just skip that last question. I don't know which one it is. Okay, I know it. But I don't want to uh keep you longer because otherwise you will be late for your next class. All right. So that is all for today. Thank you everyone. Assalamualaikum.
Waalaikumsalam. Thank you, miss.
Waalaikumsalam. Thank you.
You're
Waalaikumsalam.
welcome. Bye.